The warm-up. So in this session we see the first panel, which is the warm-up panel. This is a very important panel because it allows us to connect the optical image, optical camera image, with the space of our topography. So you see that we can select our layouts in case we want to select laser or TSPL layouts, the layouts that we created and imported earlier, and we can move them around. It's important to notice that we are using here a coordinate system. So when we move our geometry, let's say we want to move a laser, we can move them around the using the coordinate system of the warm-up or the piezo center. So in case we use the piezo center, of course, you will see that we have much smaller, let's say, distance of the center of this field because the piezo center is around here. Well, if we change the coordinate system to the warm-up, then we will see that the origin is somewhere else, which is 0, 0 is going to be around here. So here we have the center of our coordinate system. So what can we do in the warm-up? Once we have a geometry, a layout, we can select it. Let's start with the TSPL layout first. We can select it, we can move it around with this dragging function. And we can also rotate it manually. The rotation can be done at any of the corner of the field, but can also be done in this small menu in the layout. So we can either move it around the origin or rotate it with a specific angle. So we can also do eventually transformation on X and Y. Another nice thing that we can do, this in general let's say tool that we have also in the camera, is moving to a location. So once we click here, let's say we want to go here, we use this move to a location functionality, so move stage to position, and we move there with the core stage. So in this case you can see our particle that was the target of our motion. This we can also do it from the camera, so it's quite a useful tool. In general, this function, also this view of the warm-up, can be achieved only if we correctly identify the position of the tip. So now you see that we have the tip location at tip position that is been shown in the display settings. If we do not select the tip position before opening the warm-up, we will not see the camera image. So basically we will have this view. So it's important when starting using the NanoFraser to remember this simple operation in order to find the tip. I mean, using the cantilevers, MBS cantilevers, usually we have the location of the tip, which is around here. It's not very important that you select the exact location with nanometric precision of the tip. It's important that you tell the software where the tip is, because otherwise we cannot really connect the optical camera image with the warm-up. So we can use this tool, set tip position manually, and we can just press here. If we do this location, then the laser configuration will be invalidated, of course, because we changed the position of the tip. And of course, if we also have the laser and we run the procedure of the laser configuration, the tip location will be determined automatically by the software during the autofocus procedure. We can also find the tip using the utilities. So if you go to the microscope, we have this find tip position in the cantilever. We can just press it and let the software find the position of the tip using the camera image. Takes a little bit longer, but it usually works quite well. So in case you don't really know where the position of the tip is, or you're just lazy to click, you can just press this cantilever find tip position function in the utilities. Now it's still looking for the tip, and you will see that when this loading icon will become green, the tip position will be determined. So okay, it was pretty much where we set it before. So we're happy, we know that where the tip is, and we can make good use of the warm-up. Other important things that we see in the warm-up. First of all, we can select different modes. So now we have the standard mode, which is the write layout. We import some layouts, and then we can write these layouts either with TSPL or with laser in our warm-up. But we also have reading functionality, so we can read a layout, the layout that we import in the geometry can be used as a read layout, but also read arbitrary and write arbitrary. So we can decide to read or write arbitrary rectangular areas. So sometimes can also be useful, especially the reading arbitrary. Then we see here some other boxes. We can have the allow stage movement box. Once, for example, we have a layout that's placed outside the range of the piezo scanner. If we have this box unchecked, we see that the play button to start the patterning is grayed out, so we cannot do it because we are outside the range of the piezo, so we cannot perform this patterning. And why is this function usually not already checked in? Well, because if we allow the stage movement, we don't use the piezo scanner, but we move with a core stage, and this movement introduces errors. So if we want to keep the highest precision, sometimes we want to just operate in the range of the piezo scanner, which is the case of high precision overlay. So let's say we want to find a nanowire or a flake, and then we want to pattern on top of it. Ideally, we don't want to move with the core stage after we have done the reading, so the location of this we have known the location of this flake or this nanowire, because then we will introduce some errors. So then the fields that we will pattern on top of it are not going to be exactly where we want them to be. So in this case, we don't care about any overlay, any precision of stitching or whatsoever. So we can just allow the stage movement, and we can pattern even outside the range of the piezo. What will happen is that the core stage will move so that we can pattern this field within the range of the piezo scanner. We also have an automated overlay mode. We can check when we use this automated overlay function in the advanced tools, or also we can select an active field stitching in case we're using stitching, so we are dealing with splitted geometries and multiple fields. In case we want to have a more precise stitching, we can use the active field stitching. Usually the standard stitching mode is the standard stitching, which is writing, moving with the core stage, then writing the following field. While when we have active field stitching, we have write a field, then we move with the core stage, we read the margin of that field, and then we align the following writing field. So it's a read, write procedure, which is more precise in terms of stitching. Let's also have a look at the areas that we see in in this warm-up regarding the design that we import our layout. So we see different colors. First of all, the green is the extension of the piezo scanner region. Yeah, you see it's around 60 by 60 micrometers. Then we see some other regions. So first, we can also see the names in the display settings. The scan region, which is this blue region that's outside the reading or read region. And we also have the writing region. So the writing region will be our design, so our Mona Lisa. Outside the writing region, we can decide how much space we devote to the reading. So this so-called read margin, which can be changed from here. So in case we want to increase the reading margin on X and Y, we can do it. So this will increase, of course, the patterning time because we have to do more reading, but sometimes it can be helpful, especially for patterning over some topographies. And we see that we can also change different read margins for each field in case we pattern multiple fields. So what are these regions? Well, the read regions means shows all the areas of the surface that we are going to be reading when also doing writing. While the scan region is related to the acceleration and deceleration that's needed to achieve the patterning speed that we have in this region. So when we pattern and when we read, we have a constant speed. Of course, to reach any speed, we need an acceleration and then a deceleration region. We can also see that this region will be increased or decreased as we play with pixel size and pixel time. If we increase the pixel size, we will increase the speed, so we will also increase the acceleration and deceleration region. If we increase the pixel time, we will decrease the speed, so we will also decrease the acceleration and deceleration region. Just as a proof, we can see that by changing the pixel time here, let's say we put 100, so this is going to be 5 times smaller now. Press enter, and then we see that this area is much more reduced. So I can go back so that just maybe can be more visible. So now we have scan region of around 1.5 micron. I put 25, and now the read region is around 3 microns, 3-4 microns. Because we reduce the pixel time, so we increase the speed. So we can also see the fast scan direction here. This arrow shows the direction of our fast scan. Other things that we can see in the display settings is the tip position. In this case, it's here. And the approach position. So we can decide where we do the approach on our design. Let's say we want to do the approach on the margin of the right field. We go to the approach and we select here. Go back to the session, and we see that we have moved our approach. This can be useful in case we don't want to approach on a surface that maybe is not a zero reference. So let's say we have a trench, or we don't want to approach on specific parts of our sample, we can always select where we do this approach, which is I think good to know. Other things that we can see are the origin markers, so the origins for this specific field, and the field outlines in case we have split geometries. We can check this box to see the outlines of each field. Now it's not very useful, but can be more useful when we split the geometry. And here we have a refresh button for the camera image, and we can also add the captions for the right fields and the topography, and choose the opacity of either the right field or the camera. Sometimes playing around with this can allow us to do a better overlay, for example. Other small things, we can see that we can play around with the color scale and selecting the data that we display in the warm-up, because after we're done patterning, here I've done some patterns, so let's select a random pattern. Probably it's outside our range here. Okay, so it's here. This is a pattern and test pattern that I did. We can select the data that we display in this topography. And it's also very convenient to see the topographies in this warm-up, because whenever we want to go and find them again, we can just press move to location and we will move towards this pattern. And if we move here, probably we will see it also from the optical image. So it's this field, we unselect it, and it's here. So we clearly see that it was pretty much where we patterned before. Sometimes when we navigate through the warm-up, we can get lost. Let's say I zoom out too much, I cannot find my optical camera image again. Sorry, anymore. And we press the home reset zoom button. It allows us to find our tip, our cantilever much more easily than just moving around with our cursor. We also see the number of fields and the time that's estimated for patterning our design, in case we want to double check it. And yeah, this is pretty much it for the very basic information of the warm-up, how to navigate through it. Just small things that we will see in other videos maybe is the open in KLayout function, which is very useful, especially for overlay. We use usually KLayout to create GDS files, but in general you can use any software to create GDS files. But with this open in KLayout, we can open our warm-up with camera view in KLayout, then place some designs, re-import it again in the NanoFraser with the correct coordinate systems to have the best, highest precision overlay possible. So this is pretty much it for the warm-up. In the next videos we will see how to pattern with the TSPL and with the laser.